Today we're going to continue our discussion of particle mole mass conversions by adding a third conversion factor. Now this conversion factor, I kind of think of it as being parts of a whole. How many particles do we have, or how many atoms do we have of each kind of element inside a particular compound? For instance, if I told you that we had a dozen socks, a dozen pairs of socks, you might give me a conversion factor that there are 2 socks in each pair of socks in order to help you solve that problem. You need to know how many individual parts there are inside that whole. Take, for instance, something like calcium phosphate, a little more difficult one. In a compound like this, we've already established that there are 3 calciums. We've looked at other problems like this and seen that there were 2 phosphoruses here and 8 oxygens. Well, what kind of conversion factors can we make out of that? Well, we can make a conversion factor that says that there are 3 atoms of calcium for every 1 formula unit of calcium phosphate. We can say that there are 2 atoms of phosphorus for every 1 formula unit of calcium phosphate. And our final conversion factor could be that there are 8 atoms of oxygen for every 1 formula unit of calcium phosphate. So what we're doing by making a conversion factor like that is once again getting parts of a whole. We're breaking down those compounds into how many atoms of each element are in that compound. So how can that conversion factor be used? Well, let's go down to this very last example down here, where it asks how many oxygen atoms are in 125 grams of sulfur trioxide. So when you look at this, you know you're looking for oxygen atoms, but look what it gives us. It gives us an amount of a compound. So we're looking for specific atoms in a compound. And these are always, you're always going to be able to recognize this because it's always going to be atoms in a compound. And that's how you're going to know that you're going to need this type of conversion factor that we just talked about. So let's start this and see how this plays out. It's not going to be the only conversion factor we need. But if we start out with our 125 grams of sulfur trioxide, think about what conversion factor we need next. We've already done some problems where we've dealt with molar mass, our table grams per mole. We've looked at Avogadro's number, which is our 6.02 times 10 to the 23rd particles per mole. And now we're looking at our parts of a whole. How many atoms are there in a compound? So what can we use next? We know we need grams of SO3 on the bottom. Well, the only conversion factor that we have of the 3 that we can use, the only one that even involves grams is our table grams, our molar mass. So what do we need to find the molar mass of? We need the molar mass of SO3. So if we look up 1 sulfur is 32.07. So I'll do this down here kind of out of the way. 32.07 for our 1 sulfur. Each oxygen is 16, but there are 3 of them, so that's 48 for our oxygen mass. This adds up to 80.07 grams per mole for our molar mass. So let's put that in. 80.07 grams, because remember, 1 always goes with mole in our conversion factors for every 1 mole of SO3. So now we've got grams of SO3 canceling, and we're left with moles of SO3. But that's not what we're asked for. We're asked for oxygen atoms. Now, right now we've got moles of SO3. We can't go straight to atoms in a compound, atoms in a molecule of SO3. We're still at moles of SO3. So before we can do anything else, we've got to have a conversion factor in it that has moles of SO3. So 1 mole of SO3, 1 always goes with mole in our conversion factors. And our conversion factor that will change that to our molecules, like we need it to be, is our 6.02 times 10 to the 23rd, our Avogadro's number. 6.02 times 10 to the 23rd molecules of SO3 for every mole of SO3. So now we've got moles canceled. We now know how many molecules of SO3 we have, but we don't want molecules. We want to know how many individual oxygen atoms there are in that compound. Now think about what 2 conversion factors we could use. For this compound, there's 1 sulfur and 3 oxygens. So we could use 2 different conversion factors. We could say that there was 1 atom of sulfur for every 1 molecule of SO3. And what about oxygen? Well, there are 3 atoms of oxygen for every 1 molecule of SO3. And why is SO3 a molecule instead of a formula unit? Yeah, because it's got all nonmetals in it. That means it's a molecular compound, so it's made up of molecules. So looks like the one we're going to need is this one right here, because it's asking us about oxygen atoms. So that's going to be our final conversion factor, that there are 3 atoms of oxygen for every 1 molecule of SO3. That's going to cancel our molecules of SO3, leave us with atoms of oxygen, which is what we're looking for. Now when we plug this in our calculator, we're going to plug in 125, since 80.07 is on the bottom, divided by 80.07, times the 6.02 times 10 to the 23rd on top, times the 3 that's on top. When we get done, think about what our sig fig should be. The 125, our given, has 3. 80.07 has 4. The 6.02 times 10 to the 23rd has 3. And since the 3 is a counting number, it has an infinite number of sig figs and therefore does not get counted on our sig fig determination. So it looks like we need 3 sig figs, and this is going to come out to be 2.82. Now watch it. I get a whole lot of people that say 2.82 atoms of oxygen. Does that even make sense? No. Not in 125 grams of sulfur trioxide that we can measure out on our balance. 2.82 makes no sense. Look at the end of the display on your calculator for that E24, that times 10 to the 24th, because that's what we need. 2.82 times 10 to the 24th atoms of oxygen is our answer.